Okay, so thank you very much for the great honor of this award. I'm very pleased to be here today. And so in my talk, I'm going to talk about challenges we're facing for concrete and try to say a little bit about how I think we should be managing the research that we do to meet these challenges. So we can think of many reasons to do research on concrete. Here are just a few. We can look at improving properties, we can look at special applications, and today we hear an awful lot about sustainability or lowering environmental impact, and this is the main area I'm going to talk about today. And I want to talk about this because I hope I can illustrate in my talk, what are really the issues behind this question of environmental impact of concrete. And it seems like this should be well known, but unfortunately I don't think it is, because at present what I see is that much research is funded with the objective of lowering environmental impact, but most of this is unfortunately wasted on things that are totally unrealistic in practice. So this is what I want to talk about. And the first thing really to introduce is when we're concerned about sustainability. Here we're generally talking about climate change, global warming, production of CO2. And this slide here illustrates the problem that although historically the increase in CO2 level can be attributed to developed countries, today the production of greenhouse gases is really taking place much more in developing countries. And if we want to try and reach these scenarios, which are what are considered necessary to limit global warming to 2 degrees, then it would be no good if we cut all the emissions from the OECD countries. We still wouldn't be able to meet that target. And this is even more true when we come to talk about concrete, because concrete is now overwhelmingly produced in the developing world. Now, concrete gets a very bad press, and we hear an awful lot about the fact that concrete is responsible for between 5 and 10% of man-made emissions. And this is true, but this is actually a remarkably low amount considering that concrete makes up over half of everything we produce. And if we look at these comparative figures, which come from a colleague compiled for 2005, you can see, for example, if we look at steel, where the production is about 5% of that of concrete, then it still produces the same amount of CO2. But we don't hear people saying we should stop using steel. So we have to really put this in context that concrete actually has a remarkably good environmental performance. It's the fact that it's very widely available and very cheap means it's so widely used. I know I'm really treading on difficult ground putting up these figures for timber here, and these are worldwide figures. Of course, in some select small countries like Sweden and Switzerland, we have nice sustainable forests. We can harvest wood from them on a sustainable basis. But unfortunately, in most of the world, this is not the case. In India, China, Africa, wood is in very, very short supply. The estimations are that the harvesting of that wood is producing a lot of CO2, but regardless of the CO2 issue, we have to look at the overall figures. The amount of timber produced is about 10% that of concrete, and even if we double the use of timber, this couldn't even fulfill the demand of increase for concrete. So it's not really a question of one or the other. It's a question we need all these construction materials to meet demand. And concrete worldwide is going to continue to be the only material that can really be used in the quantities that is being demanded. So this 5–10%, I think we don't need to get hysterical about it either. Some people ask me questions and say we should stop building. Well, where are you going to live if we start building? And it's not only where you are going to live, who live in a relatively wealthy country like Sweden. Are you going to say that all these people in India who are sleeping on the streets, they're not allowed to have any more houses? And it's the same order of magnitude as what we produce by using computer servers. So every time you press that click for a Google search, you're producing a lot of CO2. And which would you rather do? Have your house to live in or be able to do all these searches? You know, we need to think about these issues in context and not get hysterical about this CO2 from building materials. So this demand for concrete is going to increase, and you know, this is a very realistic projection if we look at what has happened already in China in the last 10 years. So today China produces more cement than was produced in the whole world 10 years ago. And another way that is being expressed is in the last 3 years in China, they produce more concrete than in the USA in the whole of the 20th century. And we see it's projected that, you know, the demand in China is going to peak. I mean, they've put this concrete into things, not only houses, but high-speed rail links, which is going to contribute to sustainability because instead of flying everywhere, now the Chinese are largely using trains, which is a much more ecological mode of transport for large numbers of people. But we see that there are other countries which are trying to follow this development path, notably India. Today in India, the consumption of concrete per person is 6 times lower than in China. So even if it doesn't reach the levels we see in China, even if it only reaches half that level, they're still going to be producing in 2050 3 times more cement than they're producing today. And of course, there are many, many other countries in South America, in Africa, in Southeast Asia, etc., which are also set on the same path of development. Here's an example for India, that India wants now to really develop this corridor between Delhi and Mumbai. These blue dots are all the new cities they intend to build. And the only way you're going to be able to build these new cities, of course, is by using a lot of concrete. So I really want to emphasize at the outset that we shouldn't be negative about concrete. It's really the only viable solution and we want to continue to reduce the environmental impact, but we have to be able to satisfy the growing demand for construction materials. So what are the options for improvement? Now, if we look at the production of cement, which of course is the main contributor to CO2 in concrete, what we see is that 1 ton of cement leads to between 650 and 900 kilograms of CO2. But it's actually unique amongst man-made materials in where this CO2 comes from, because only a minority, 40%, comes from energy. So many people think that the answer to all our problem is renewable energy, and of course renewable energy is incredibly important, but this isn't going to help that much in the case of CO2 emissions from concrete. This cement kiln here looks rather sort of rusty and perhaps not very sophisticated, but this belies the truth, as there's been incredible progress in the efficiency of making cement over the last 40 years. And now the best plants are operating at something like 80% of the thermodynamic limit. And all of you who studied thermodynamics will hopefully remember that it's never possible to reach 100% efficiency in a thermal process. And to put that in context, if you look at, say, electricity production, the best state-of-the-art power stations are not reaching this 80%. They're more in the range 60 to 70%. And furthermore, this cement plant is a very flexible tool which can use doesn't have to use fossil fuels, can use waste plastics, waste oils, many other things that would be quite hard to dispose of safely in any other way. So not only can these wastes be disposed of safely, but their calorific value can be put to good use. And typically in Europe, plants can operate at more than 80% of waste materials. So if really we're going to cut CO2 emissions from cement, we have to look at this other side of the pie, which is this 60%, which comes from this very simple chemical equation, which is calcium carbonate or limestone, which is the main raw material for cement, which when you heat it up, breaks down to calcium oxide and CO2. And it's that CO2 that's given off that produces about 60%. Now, this leads to another problem, which is if we're going to reduce this CO2 here, we'll inevitably have to reduce the amount of calcium. We'll inevitably have to change the chemistry of the cement. And if we change the chemistry, this will mean that the whole way it reacts and performs will maybe change, and we have to do research to examine that and to check that the material is still fit for purpose. And that's very, very important, and one of the reasons why change is so slow, because of course if you're building a building which is going to last for 50, 100 years, you need to be sure that the material is going to last that long. Now, if we want to change this chemistry, we're quite limited in the options we have by the composition of the Earth's crust. And for me, it's always staggering to realize that only 8 elements, that's to say oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium, these 8 elements make up more than 98% of the Earth's crust. So this all comes from the way stars burn, and so there's nothing we can do about it. It wouldn't even help if we went to another planet. It would be much the same story. But clearly, this means there's not much point looking at all the elements in here for cementitious materials, because they're not going to be available in large enough quantities to produce concrete. For example, we read a lot in the press about the shortage of a lot of rare metals, say iridium, for producing flat screens. And clearly, if you haven't got enough iridium to produce your computer screens, you're not going to have enough to produce concrete. But in a sense, this is quite a good thing, because it means we can exhaustively study all the different options we have for cementitious materials. There's no stone unturned. And that's a very important point, because, you know, many people think there's some magic solution out there that we just haven't found yet. And what I want to convince you of is no, there isn't. We know all the possibilities, we just have to select which is the most appropriate. And if we look at these 8 elements, which are in cementitious materials in the form of oxides, we can see which ones are really suitable for producing cement. And here, this is this sort of basic scheme of how cement works. I hope most of you kind of know this at any rate, but at the beginning, we start with this grey powder in water. And we have these grey grains of cement, which aren't linked together and which can move around freely. You can put the concrete in place. And then we get this chemical reaction, which, if we stop to think about it, is almost magical in the way it works, because what happens is we have a reaction between the water and this grey powder to produce this red stuff in this picture, which is the hydrates, and the volume of that hydrates is about twice the volume of the grey stuff in the beginning. So the extra solid volume produced can fill in the space between these cement grains, can link them together, and can transform the material to a strong solid, containing pores, but nevertheless with very good strength and durability. Now, to do that, we need to have compounds that can be transported in the water and move through space. And if we look at those oxides we have in the Earth's crust, if we look at the alkali oxides, sodium oxide and potassium oxide, these are basically too soluble. So they don't deposit in space. If we look at iron oxide and magnesium oxide, we have the opposite problem. These have too low solubility. So to illustrate that, here's a 30-year-old concrete. We can still actually see where the original cement grains were. And all these little bright areas here, this is where the iron oxide was in our original cement. And in 30 years, this hasn't moved anywhere. So it's not doing any harm, but it's not really contributing to the strength development, because it's not moving out into the space and filling the space between the grains. And similarly for magnesium oxide, this is a picture of a slag blend. So these are slag grains. And you see around the slag grains, there's been a reaction, and there's this dark rim. And the reason there's this dark rim is because that's where all the magnesium is. So again, the magnesium that was in the slag is just stayed in exactly the same place. And it's all the other elements that have moved out and have filled in this space between the grains and give the material its strength. So basically, we come down to these 3 oxides, which are just right. Okay, so we only really have to focus on this system. which is of course very well known to cement chemists, because now if we look at this system of silica, calcium oxide and alumina, we see all the compounds that we know are used in cements. We see Portland cement here, which is very rich in calcium. We see slag, we see fly ash, we see metakaolin, natural pozzolans, etc. And generally speaking, we see that these other things, they have less calcium, but that means they're less reactive. So, you know, that's a little bit of a problem I'll come back to. And of course, these materials are now widely used in cement in blended cements. So this has really been a very, very successful strategy that has been adopted by the industry in the past decades, that we have already optimized the process, and now it's moved from cement being a question of clinker, which comes from the cement kiln ground with gypsum to give cement, to the incorporation of these other things, which are collectively called supplementary cementitious materials, which may be fine limestone from the quarry used to make the cement, which may be fly ash from the production of electricity from coal, it may be blast furnace slag from the production of iron from iron ore, natural pozzolans, etc. And if we look at worldwide figures, we see that overwhelmingly just three things, limestone, slag, and fly ash, make up the vast majority, about 80% of the substitutions for clinker. And if we look at these figures, which are from Holcim, but would be similar figures for any big cement manufacturer, we see that over the past decades, the amount of clinker on average in cements has been reduced by about 10%, and that 10% reduction is roughly equivalent to a 10% reduction in CO2 per ton. So what's the problem? That's a very good strategy, but we see that it's kind of leveling out here. And it's leveling out partly because of technical performance, but much more because of the availability of these materials. And this is something that most people don't realize. The amounts of blast furnace slag and fly ash, etc. we have are really quite limited compared to the amount of cement produced. So the amount of cement produced in 2013 was about 3.6 billion tons. The amount of blast furnace slag was about 5% of that. So we know we can make blends containing 70% slag, but we don't have anywhere near enough slag worldwide to make all the cement at anywhere near that level. And I'm going to come back to that. You know, slag, it's great. You can put almost as much as you like in cement, but we simply haven't got that much of it. And nearly everything that's being produced is already being used in blends in concrete. So all the potential of slag to reduce CO2 is already being realized. Fly ash we have slightly more of. There's not so much used because the problem of fly ash is it's got a very high variability. So not all fly ash is suitable. And this problem is actually getting worse because environmental regulations for producing electricity means that now some of the processes mean that fly ash is contaminated with things like mercury, which means obviously you don't want to use it in cement. For example, in the USA, where they now have abundant reserves of shale gas, fly ash is going into short supply. You know, so these substitute materials have been very successful, but we can't go further with them. So where can we go further? And here we're really limited because there just simply isn't anything else worldwide available in the kind of quantities we're talking about, except this thing I put calcined clay. And I put this next to metakaolin, but we're not actually talking about pure metakaolin, which is a rather expensive product because it's used to treat paper and things like that. We're talking about low-grade clays, and I'm going to come back to this point. Now, if we look at what are the prospects for reducing CO2, this is the study that was done in the Cement Sustainability Initiative of the World Business Council for Sustainable Development. And what they did, they analyzed all the available technologies and said, how far can this go in reducing CO2? And not reducing CO2 per ton, but overall for the whole of cement production. And this is for a low demand scenario, this is for a high demand scenario. And basically they said, well, look, we've got this technology of using waste fuels. If this is implemented everywhere, so I told you in Europe we have about 80% substitution, but in India the level of substitution of fossil fuels is about 2%. So clearly, of course, if we can transfer that technology everywhere, we can make gains in terms of not using fossil fuels. If we can improve efficiency, if we can continue to replace old, inefficient cement kilns with new efficient ones, then we can save this red one. And this kind of comparatively thin green line is what we can expect to get from continuing to use supplementary cementitious materials. So the amount of slag and fly ash available will increase. It's estimated from about 500 million tonnes in 2006 to about 1.2 billion tonnes in 2050, but that can only make this this relatively small contribution to CO2 reduction. And so in this study, they said, well, okay, we're going to go for carbon capture and storage. Well, that's very nice to say, but even if you leave aside the technical issues, and we know there are a lot of technical issues with carbon capture and storage, if you just consider purely on price, this would mean that the price of cement would increase about 3 times. Okay, now in Sweden, maybe your government comes along and says to all of you, you've got to pay 3 times as much for your cement, and you're not going to like it, but probably people could afford it. But in India, where incomes are that much lower, where they say, well, look, the CO2 problem worldwide isn't our fault, are they going to impose a 3 times increase in the price of cement? I don't think so. So I think, this is totally unrealistic. It's not going to happen because of geopolitical and price situations. So there's really no magic solution. There's really very few alternative materials available in the quantities available compared to Portland cement. And, many people, every day in the press, you can't see this new, supposedly magical solution. And when you analyze it, these are going to be, at best, niche products, which really have no significant impact. I mean, if we look at the example of calcium aluminate cements or calcium sulfur-aluminate cements in China, these are materials that have been around for 50, 100 years and still only represent 1,000th of the production of Portland cement. So they're not really, significant in terms of CO2 production. And here I really want to talk about the absolute fallacy of alkali-activated materials. Because, this to me has been the greatest con of the last 20, 30 years. Why do I say that? Now, for those of you who don't know, alkali-activated materials are where we have things like slag or fly ash, exactly the same slag and fly ash we've been talking about, which are activated with alkalis. So there's no clinker in it. People say this is clinker-free cement, so there's no CO2 associated with that. And these were developed back in the 1960s in Ukraine, and they work. I mean, there are still buildings in the Ukraine built with these materials, still standing there, perfectly okay. So it's not a problem, they work. They're also called geopolymers. You may know that term. But the problem is, there's 2 main problems. The first problem is that they're totally non-robust materials. So they're very sensitive to very small variations in raw materials. And this means that, you can't just give them to any old construction worker and expect them to work. And in practice, that will mean that they will never come to the market at a price which is anywhere near that of Portland cement. It'll probably be 2 to 3 times more. But more importantly, we've just seen that these raw materials we're using to make these are in short supply and are already fully used in concrete. Now, CO2 balance is questionable. Nobody's managed to make them work in the last 50 years. Handling strong alkalis on site, durability issues, these are all other issues. But basically we come down to this choice. You have a source of slag or fly ash, for example. What are you going to do? Are you going to use it in a blend? Well, why not? Because everybody does, and we have very good experience, and it performs very well. And we know that it's going to be durable. We've done tests on that, no problem. And the fact it's in a blend with Portland cement clinker means that really it behaves the same every time. We can give it to construction workers and they can use it no problem. It can be used in a ready-mix plant, no problem. Uses existing technology. Or are we going to use it in alkali-activated materials, where in fact the CO2 reduction is questionable because people don't take account of the fact that alkalis produce CO2. They have totally non-robust behavior, so you may have setting times going from 5 minutes to 5 days. You've got to get people to handle strong alkalis, 5 molar solutions on site. The production of alkali world is not actually enough to make a significant level of substitution, and the durability is questionable. So which are you going to do? And even if you did choose to make alkali-activated materials, because the only one that really works at room temperature is slag, and because all of that slag is already used in blended cements, you're not actually going to be helping CO2 reduction at all. In fact, you're going to be making it worse, because you've got to put in the alkalis, which produce CO2. So, you know, this is a complete backward step. And we are investing millions in research on these materials. We have got to stop. Now, what do I think is a more realistic solution? Well, I think what we've got to look at is analysing the world's resources. We see the only material potentially available in viable quantities is calcined clay. And what we're working on in our laboratory is we've shown that blends, when you take calcined clay together with limestone, are particularly interesting. And this has led to a very big, well, rather big project supported by the Swiss government through its Agency for Development and Cooperation. And if we look at this rather schematic geological map of different geological areas, we know we're going to have suitable clays in the areas which are kind of yellow and lime green. We're going to have suitable clays in all this region of the world, which is exactly where we have developing countries, which is exactly where the demand for cement is coming up. Yeah, we're not going to be able to make them in Sweden, but demand for cement is not going up in Sweden. It's pretty static. Same for Switzerland, same for most of Europe. But in China, India, Africa, South America, all of these have very interesting reserves of these materials. And often, the reserves are like this. That's to say, we don't even have to open new quarries, because in these countries, already clay has been mined. It's been mined for making china, and only the high-grade stuff is good enough for making china. So all the low-grade stuff just gets mounded up in these heaps, where, you know, somebody's got to think what to do with it. And this material in these heaps has perfectly enough kaolin material to be used in blends and cement. So what is this LC3? Well, this LC3 stands for limestone calcined clay cement. We're just talking about facts here, what it contains. And we know about pozzolanic action of calcined clay. It's like fly ash. We can take a mixture which would have, say, 70% clinker and 30% calcined clay. But by using together calcined clay and limestone, we can go a lot further. We can go to 50% or so substitution. And at that 50% or so substitution, even at quite early ages, we can get strengths that surpass that of the Portland cement. So we've got half the amount of clinker, half the amount, well, not quite half the amount of CO2, but 30% less CO2 with higher strength. So this is really interesting. You know, this is like what we should be looking at. And just to go into a bit of the chemistry, what's happening here is that we have reaction of the aluminate compounds in the calcined clay, which react with the limestone in this reaction here, for those of you who are interested, to give us this compound which is called monocarboaluminate. And this monocarboaluminate, it's like monosulfate. We have monosulfate in ordinary Portland cements. We actually have that monocarboaluminate in most cement we have today, because practically all cement contains at least 5% limestone already. But the point is, when you add in the calcined clay, you've got more alumina, so you can react more limestone and you can go further. And the strength you get really just depends on the kaolinite content. So here we see, we see a very nice, fairly linear correlation with the kaolinite content. And what you see here in these dotted lines is this is the strength of the reference Portland cement. So this says that at 7 days, which is comparatively early, you can use a clay with a kaolin-like content of 40% and still get the strain strength as the straight Portland cement. So 40% kaolin-like content, that's the kind of material that's thrown away today. You can blend it in cement, you can get rid of about 30% of the CO2 and the same strength. And of course, then you're going to say the same, do you have the same durability? This is ongoing research, but the first results look very positive. And if we go back to these graphs here, what we now see is that if we can increase the supply of supplementary cementitious materials from, say, 1.2 billion to 1.8 billion, which is quite realistic given that map I showed you of the availability of these materials, it's not, you know, completely stupid estimation, we would increase this rather small green line to this big contribution. So just by using calcined clays, we can contribute this much more to worldwide CO2 production. And that's about 300 million tons per year, which would be like wiping out the whole of the CO2 emissions of a country like France. So that's not insignificant. And that's, in my view, worth investing in. And worth investing in means that, you know, it's a nice idea in the lab, but can you do it in the field? And the answer is yes, because we've already done it in the field. And we've already done it in the field in very non-optimized conditions. And that's very important, because again, if I go back to alkali-activating materials, they work very nicely in the lab, and then you go to full scale, and you have to be awfully careful to make sure that everything's done exactly right. Well, in this trial in Cuba, unfortunately, not everything went exactly right. This is a rather old Russian-built kiln, and when they started doing the calcination, the shell started melting, they had to patch it up, you know. You can see down here, there's an awful lot of kind of rather dubious material that got mixed up in the clay. So, you know, I was thinking, this is terrible. We spent 5 years trying to get to this point of doing an industrial trial, and now there's just this horrible mess. But my colleague in Cuba, who is much more optimistic about things than me, took it to the local pre-stressed factory, and no problem, they could make perfectly nice concrete. And to test the durability of this concrete, we now have, well, we've built houses out of it, but we also have these nice concrete blocks exposed off the beach in Cuba. Anybody who likes can go and visit it. It's right next to a very nice resort. And so far, everything looks very good. In India, we had an even worse time because we only wanted to make a few tens of tons. And the best kind of tool we could do it was to use this static calcination. You can see this oven here isn't all that sophisticated. In fact, the calcination in some cases was only about 50% complete. Nevertheless, we made the cement, we gave it to unskilled workers. This is somebody making these micro-concrete roof tiles, which are made in local workshops for local housing. Here are the roof tiles. And all our materials outperformed the material they were using every day, which was a fly ash blend. So this is a fly ash blend here. These were all the cements we produced. And even though in some cases we had to use slightly more water, we still had higher breaking strength for the roof tiles. So, you know, first off, trial, we knew it wasn't perfect, but still it works, and you can give it to totally unskilled people. And we went further, making all these blocks, and here's a house. This house is built totally of LC3 materials, and it was estimated, even compared to existing solutions like fly ash blends, another additional 7 tons of CO2 was saved in building this house. So that's kind of where we are. We've got a lot of work to do because even though you've done these demonstrations, the industry is very conservative. There are things like standards to look at. We have to look more at durability. As I said, our first results are all looking positive. And it's not like we've got a totally different chemistry. We've got a chemistry, we've got basically CSH there. We've got these AFM phases. We know about all of that. We know how they behave over time. We have a good porosity. We've measured all of that. So there's no reason why we expect the durability to be a problem. It has to be tested, it has to be examined. We have to look at things like shrinkage creep and cracking. Again, we started work on that. First results look very positive. We have to look at workability and rheology. Sometimes this can be an issue, but most of the time you can make perfectly good concrete without any particular change in the formulation. So this is all ongoing, and it's really an international program. We have this funding from the Swiss government, and most of this funding is going to India and Cuba, with some going to EPFL. But we're also developing partnerships really internationally with Thailand, China, Brazil, South Africa, etc. So I hope that's shown you what sort of thing we can do. There is hope, we really can do things, but we need further research. And we need further research because with all these blends, the problem really is, the limitation in their use is early strength. So this shows 7-day strength for a number of blends with fly ash and all these kind of things. And you can see when we get above 10-20%, generally the early strengths are lower. These ones up here, these are our calcined clay materials, needless to say, which of course look very good, up to about 50% replacement. And the reason for this is that early reaction is totally dominated by the clinker. Here are some calorimetry curves which show the reaction kinetic of a plain Portland cement, and then of the Portland cement part in a blend with quartz and with slag. Okay, so we've re-normalized this curve. Of course, if you put in 40% slag, of course you get a lower heat. But the heat relative to the amount of clinker you've got there is a bit higher, and that's because of the physical effect of putting these materials in. But what you see here is for the first 24 hours or so, whether we put in quartz or whether we put in slag, it's exactly the same story. That, quartz is obviously inert, that it's just the physical presence of these particles which slightly enhances the reaction of the clinker component. And only after the first day or so do we start to see a slightly higher heat here from the slag, because now the slag's starting to react. So if we want to address this early strength problem, we have to actually go back and look at clinker reactivity. It may sound ironic that, we've talked about supplementary cementitious materials, but if we want to go further, we want to be able to substitute more, we have to be able to increase clinker reactivity. And there are ways of doing this, and this is where we should be looking. We should be looking more at optimizing the particle size distribution. For example, if we could have the clinker in the fine particles and the fly ash or whatever, or the slag or whatever in the coarser particles, then we'd get more reaction early on, and the slag reacting more slowly, it wouldn't make that much difference to the amount of reaction. Or maybe we could dope with other ions. So here's some interesting work we published last year in collaboration with some Chinese researchers, where we had halides that had minor dopings with zinc. And you can see that here in this heat curve, in this first day of reaction, we get twice as much reaction of the ones doped at zinc, and we control for the particle size. So just putting in this small amount of zinc seemed to increase the amount of reaction in the first day by a very considerable amount. And we could actually relate this to the way the CSH was growing. These are TEM pictures of my student, and here's the CSH, which is formed in the first day. And what happens with zinc is you seem to be able to grow that CSH more, and you can actually see that the zinc is incorporated in the CSH. So there are other lines of research which we need to follow up. This will take time, but we're starting to work on this. I think the other thing is we really need a public campaign to better inform people about what is the real issues in sustainability. And to this end, we formed a task force under the auspices of UNEP, United Nations Environmental Programme, bringing together about 30 experts worldwide. Half of these came to our inaugural meeting in Paris in March. And with this group of people, what we're trying to do in the next year to 18 months is write a series of white papers and a comparative overview to address very practical issues about how do we sort of really get the best technologies appreciated by users in the field? How do we interface with structural engineers? Where can we really look for improvement? What's the real ratio of using cement in bags to bulk in different countries? How can we really evaluate eco-efficiency and how can we improve codes? And then the different potential solutions people have come forward with: alternative clinkers, alkali-activated materials, calcined clay, admixtures, better packing to reduce the cement content in concrete, maybe using concrete without steel, you know. So all of these things that have been suggested, we need to evaluate on a comparative grid. So that's hopefully given you some idea of where I think we should be going. I mean, I hope you really kind of start to appreciate that if we're really going to impact sustainability, we must develop new solutions for developing countries. It's no good sitting in our nice little countries like Switzerland and Sweden and saying, well, we've got everything working nicely here. If we don't help these countries with our research capacities, then we're not going to be able to contribute to this problem of CO2 reduction. Solutions must be practical. If they're really going to be taken up, they've got to use existing production tools. There's not enough capital in the world to completely replace existing cement plants with some other exotic technology. And the materials produced must be usable in the field, often by unskilled workers. In that regard, I think calcined clays and this LC3 technology have a huge potential. Probably not the only thing, but it has a big potential, and they're amazingly robust materials, which can reduce CO2 emissions by 20 to 30%. And also, I didn't really talk about this, I didn't have time, in many countries like India, in fact, we're running out of things like limestone. And using this technology like calcined clay, you can produce twice as much cement from the same amount of limestone. You have relatively low costs and reduced capex, and therefore I think it's an important technology to allow emerging countries to develop while minimizing environmental impact and resource depletion. And with that, I'd like to thank you for listening and hopefully answer questions if you have any. No, I'm not saying stop introducing fly ash, just the opposite. Continue using fly ash. All I'm telling you is it's not going to take you that much further than we are already. We're using a lot of fly ash, which is great, but we don't have much more suitable fly ash to expand that. So we've got to go on using fly ash.
Use it in the countries what we have.
Yeah, exactly.
Use the clay.
Exactly. So we need all these materials. And, you know, I mean, CO2 is being worked on in other senses. I think more promising perhaps nowadays is what people are doing in trying to transform CO2 into things like methanol and then you reuse it as a fuel. You know, this can be more interesting. But that's being done, I mean, that doesn't have to be done by the cement industry because it's a sort of more a chemical problem which has been worked on by chemists, and that's all very good. You know, I mean, if we're going to solve the CO2 problem, we're not going to be able to solve it with any one single technology. We've got to do everything. We've got to work on alternative energy, we've got to work on electric cars and concrete. You know, so it's all of these things. It's not one or the other. But some things we're doing on concrete are never going to help reduce CO2. Fly ash is great, but this alkali-activated story is something else. One at the back there.
You dismissed the carbon capture because of the price tag.
Yeah.
But that leads to another interesting issue. What is the price tag for this LC3?
That's an interesting question. The short answer is that if you've got the right location, and as the previous person said, you've got different technologies depending on your location, it can be cheaper, you can reduce costs. And that's very important because at the end of the day, the thing that's going to drive people to take up a technology is if they can reduce costs. I mean, that's why people are using fly ash. I mean, they say they're using fly ash because it reduces CO2, but honestly they're doing it because it reduces their cost, you know? And let's not beat about it, and business is business. You know, businesses need to make money. That's how the world system works. But, you know, the good news is that in places where we've evaluated it on a cost-per-cost basis, it can be cheaper. And clearly where it's not cheaper, you're not going to do it.
Yes, I wonder what temperature do you have to reach for this calcination process?
Yeah, the temperature you need is between 700 and 800. So you have got some energy you have to expend there, but it's about half what you need to make clinker. And that's also where this synergetic substitution with limestone comes in, because you can then put in 15% limestone and you don't have to heat that limestone at all. Limestone's kind of almost a freebie because all you've got to do is grind it up and there's almost no energy demand. So that's why if we go down to 50% clinker, we reduce CO2 by 30% rather than 50%. But we have evaluated all these figures.
And Karen, you have promised that we can provide the slides.
Yeah, yeah.
Slides. Anybody's
Anybody's welcome to the slides.
Yeah.
You know, get the message out to as many people as possible is my my strategy.
Okay, no more questions. Well, thank you once more.